Okay, so after understanding the general idea of what concavity means and what it means to be concave up, second derivative positive, concave down, second derivative is negative, we jump right into the calculus and the algebra of how to determine this. So we'll look at number 5. 5, we start with y is equal to x squared minus x minus 2. Now this is a parabola, and any parabola I can tell you right away that it's going to be concave up for all x. But let's see how we determine that from calculus. First we need the first derivative, which is 2x minus 1. We're not going to stop there and find where the first derivative is 0. We're not really working or concerned with the first derivative at this point. Now, instead, we're going to go right to the second derivative and find that the second derivative is just 2, which is greater than 0 for all x, and therefore concave up for all x. It's that simple. All right, we showed that the second derivative is always positive, therefore the function is always concave up. Let's look at number 7. 7, we have g of x is equal to 3x squared minus x to the third power. We find the first derivative, and that is 6x minus 3x squared. We don't stop there. We go right to the second derivative. Second derivative is 6 minus 6x. Now, this one is not as simple as the previous one, but now we're going to do what we did for the first derivative, or trying to find out where a function was increasing or decreasing. We're going to set that equal to 0. Now, and we find that that is equal to 0 when 6x is equal to x, 6x is equal to 6 rather, or x is equal to 1. Now, 1 is no longer called a critical number in this case. With the second derivative, when the second derivative is 0 or does not exist, we call that a potential point of inflection. And we'll see what a point of inflection is. A point of inflection is a place where the concavity changes from up to down or down to up. Just having a second derivative 0 or not existing is not guaranteeing us that that will happen. But let's see what we find here. So as we did previously with increasing and decreasing, we made a number line, only now we're not working with the first derivative, we're working with the second derivative. And our second derivative is here. And we're going to plug, well, we need some test values. We can use 0 to the left of 1 and 2 to the right of 1. Plug them into the second derivative. We get positive and negative. So 1 is a point of inflection. Point of inflection because not only is the second derivative 0 there, but because concavity changes. So a point of inflection is a point, it's an actual point on the graph. it has to be in the domain of the function. A point of inflection is a point on the graph where the concavity changes. It might change from concave up to concave down, or concave down to concave up, but in order to be a point of inflection, the concavity must change at that point. And it will either be a point where the second derivative is 0, or where the second derivative does not exist. Now we'll do problem number 9 here. Number 9, we start with the function f of x is equal to negative x to the third plus 6x squared minus 9x minus 1. F prime of x, first derivative, negative 3x squared plus 12x minus 9. Second derivative is negative 6x plus 12. And we're done with the second derivative. We set the second derivative equal to 0, and we get 6x is equal to 12, or x is equal to 2. So we make our number line, and our potential point of inflection is x equals 2. We note that we're working with the second derivative. We highlight the second derivative. That's where we want to substitute a value to the left of 2. 0 is fine. To the right of 2, 3 is fine. When I plug in 0, I get positive. When I plug in 3, negative 18 plus 12, I get negative. So therefore, let me just make a note here, because this particular question is not asking about points of inflection. Future questions will. I'll still write here x equal 2 is a point of inflection. What these questions are asking is to find the intervals on which the function is concave up or concave down. Now, just like we marked up the graph for the first derivative, when the second derivative is positive, that means we're concave up. When it's negative, we're concave down. Positive, concave up. Negative, concave down. And so I can say in these cases it's more simple. Concave up from negative infinity to 1. Concave down is from 1 to positive infinity. With problem number 9, concave up from negative infinity to 2, concave down from 2 to positive infinity. And for number 5, concave up was from negative infinity to positive infinity. Now you could also graph these on your calculator, and you could easily see where the concavity falls there. And that'll do it for this video. We'll go on to the next problems in the next video.